Good morning and welcome. Thanks very much for joining us on this second in a series of 4 presentations on the evolution of regression from OLS to GPS to Mars with hands-on with the Salford predictive modeling software suite. So I'm Dan Steinberg, and I'm going to be reviewing with live walkthrough of some of the main concepts that we covered last week. So as you recall, there was a brief review of the regression problem. We did some classical statistical least squares modeling of a data set. We went through the ridge, lasso, and generalized path seeker modeling of ideas and followed that with Mars. We're going to continue in 2 weeks from now with CART, random forest, tree-net, and hybrid models. Perhaps we'll say more about that later, but today we're simply using the SPM software suite to review the things that were covered theoretically 2 weeks ago by Mikhail Golovnia. Okay, so we're going to be working again with the same data set. It's rather small. This is not intended to showcase anything about the software per se. It is a well-known data set. It's easy to understand because it's about housing values and about quality of life indicators that might be driving or responsible for differences in the typical values of census tracts in Boston in the early 1970s. The data came from several different data sources which were close to, but not all the exact same time, but near to each other. And that included things like crime rates, the zoning of the neighborhood, and crime rate, and other matters that you see here. So anyway, you can read more about that, and also you can access a link to the original paper from 1978, which is a very interesting read, and I do recommend it if you're interested in this general topic. Okay, so let's go on now to the software. So presumably you have all had the opportunity to download and install the software. If not, we welcome you to do that anytime soon. It is a no-cost license. It'll operate automatically, I understand, for 10 days. You can then request a 30-day evaluation license. Contact with us if there are any other aspects relating to your own desire to evaluate or experiment with this software. So let's go on here. I'm trying to find my mouse here. And we're going to open this Boston data set. Just to remind you, with the software, if you have another file format, you can access any of the file formats that you can see there. Those are all the major statistical formats, including Excel. There's the R workspace and SAS and SPSS and others. So you can also go via ODBC, but you will probably need some help from a DBA in order to get the connection string right. So let's open this little data set here. The first thing that you will notice is just a little bit of metadata. We see the name of the file, where it's located, the date in which it was created, the variables that are on the file, number of records, the number of variables, number character, number numeric. What's that for? Mainly just to allow you to confirm that you've actually opened the right file. You can go further and view the data if you like. That'll be a read-only view, like an Excel spreadsheet view of it. You can get summary stats, some histograms. You can go into a programming mode. Let's go directly into modeling just because of the short time that we have available to work together. So to remind you from last time, and if you're here for the first time, then we are going to be using this median value of a home in a neighborhood. So the unit of observation here is a whole neighborhood. So what is typical of that neighborhood based on these other available predictors? You do not have to indicate what is going to be a predictor. If you don't, then we will assume that it's everything. Let's just be explicit here though. If we click the column header and then click down below, everything is selected. Okay, what modeling engine should we use? If you look to the lower right part of the modeling dialog, you will see an area called Analysis Method and a drop-down menu. So these are the major engines that are available to you. Let's go ahead and choose Regression for right now, just to remind ourselves of what will happen there. And because we're working in a data mining environment rather than classical statistics, we're always going to insist on having some data held back for testing. This data set's not that big. I don't want to put a whole lot of emphasis on the results that come from this particular random selection of 20% for testing, but it is a decent way of illustrating what we're doing. So just to remind you again, we've got regression here. We don't have any choices up here just yet because regression is regression. And we've got 20% held back for testing. We're going to hit the start button. And so what do we get here? By the way, if you're interested in classical style reporting, that's all available here in the what we call the classic output window. And you'll see here things that look rather familiar to anyone that's worked with the old style regression packages. So there's a lot more that's reported down below. We won't go to that now. In the GUI, we get a very quick review of some performance stats. We're just interested in the test performance here. You can see that the mean squared error on the test or prediction squared error is 27.06. So we'll just keep that in mind. Also to remind you again, what did the residuals look like here? So we have a maximum residual of 26.7. The smallest is 18 point something. You can see this spread is actually fairly large. Okay, so what we want to do now is move on to a modern data mining methodology, and we're going to start with Mars. In this case, we're doing things in the opposite order than was done 2 weeks ago. We're going to finish with the regularized regression. We'll start with Mars. So let's choose the Mars modeling engine here. And one of the things I want to emphasize with the way the software is designed to work is that largely you can ignore all of the options, all of these other tabs that you have here. They give you a lot of extra power, but you don't have to try to learn everything at once. You can simply begin with how things work out of the box. I just want you to confirm that we actually do have the 20% random sample for testing. It's always going to be the same 20% random sample if you use that methodology for selecting it. This way you're always going to be comparing apples to apples when you run these models using different settings. So let's go ahead and run the Mars model and just see what happens. And before going into the details here, let's bring up the summary display, which is organized to look very much like the other one that we brought up for regression. So we should have the two of them. We can look at them side by side. And so we've got a summary display for regression, summary display for Mars, and look at what we get for the mean squared error here, 14.66 versus that 27. So that's pretty dramatic. And this is just straight out of the box. We haven't really tried to do any kind of tweaking or interacting with the results. And by the way, this, in my opinion, is fairly typical of the kinds of benefits that you can get from a Mars model. Let's have a look at that residual box plot. You can see how much tighter it is than we got from the regression models you'd expect. So let's see if we can see those two things side by side here. Let's make this a bit bigger. Get us some extra space. Okay, so what exactly happened when we ran the Mars model? So the best way to understand what a Mars model is to click on the curves and surfaces. So what I have here is a graph corresponding to all the most important variables that Mars selected into the model. And let's go ahead and use the show all, and we will get some what are essentially dependency plots. These are plots that show what Mars did with the predictors in order to get the good fit that we just saw. And the Mars methodology is always the same. It takes variables and it breaks them into regions, and then it applies the conventional least squares regression fitting methodology to the regions, but it allows separate slopes within the regions. So that's the simplest way of describing it. And so I'm sure many of you that have run classical regression models have occasionally attempted to build this kind of spline manually, or you suspected there might be such a thing and you did this for a specific variable. But what Mars does is it does this automatically and searches for the best location for these splits in all the variables simultaneously. And so as we click down here, we can see that some of the variables were not transformed at all. That is, they were allowed to enter linearly, but most of them were given some kind of modification, having at least two different regions for the slope. Okay, so a little bit more understanding of what actually went on here. Let's go ahead and go back to the main display for Mars, which was over here. So what did Mars actually do, and how did it get here? Well, I'm going to now ask you to click on the classical output, because this is a piece that we don't normally show. We leave it for the more expert user. What Mars does in building up its model is it goes through a process of what we call forward stepwise knot placement. So think of it like a stepwise regression, which is what it is. But before allowing any variable to enter into the model, Mars first also looks for a way to split that variable, that is, to divide it into two regions. So if the variable has not yet entered the model, it's not going to be allowed to enter until two regions have been identified. So we search for the best possible split point. We search every variable for its best possible split point. We select the best of the best, and that becomes the first step. And so that's what we see here, that this predictor, which is the percentage of the population that is lower socioeconomic status, that there is an important divide when that fraction hits 5.91. That's our best point estimate of that knot. And we then enter that into the model. So this is now a variable with a split point, and it has two different slopes, one before the knot, one after the knot. Then we repeat the process again, looking to see which additional variable might enter the model in this split way. By the way, Mars does not require that every step introduce a new variable. A step could take an existing region and split it once more. So the process is recursive in the sense that once a region has been defined, then it is eligible to be split again into two regions. In this case, we didn't see the same variable being split more than once. Here is the forward stepping. So the forward stepping actually leads us to the largest model. We call it the maximal model. And that is over here with 15 terms in it. Why 15? Well, that happens to be the default. I'm not going to suggest that you want to use that default always. It's not a bad starting place. It is a control parameter that we encourage you to experiment with. It's not clearly going to be ideal for all problems. But as a first quick way of looking at your data, it's not a bad default. So we start with that maximal model, which was arrived at with our forward stepping. What happens then is we do back stepping. So here we are with 15 terms in the model. I'm using my arrow keys now, or I'll click here. This will reveal to us the details of a 14 variable model. What 14 are there? Well, we start with a 15 and we're going to drop the one variable that Mars has created and entered into the model. We're going to drop it using criteria very similar to traditional backward stepwise linear regression. And then we were going to continue. We're going to go 14, 13, 12, etc. And we're going to actually backstep all the way to nothing, which is a model that has no regressors in it at all and just a constant. So the backstepping is clearly not confined to use the same order as the forward stepping. So we're going to backstep, and then the backstepping after going all the way to nothing is going to yield to us a candidate set, in this case of 15 different models. Which one is best? Well, if we use the test data set and we look at the prediction squared errors, then it turns out that the best model in this case is the one with all 15 terms. The GCV is an internal way of evaluating the model without reference to the test set. These two measures are usually similar to each other, and the GCV can be used if you simply cannot afford a test sample at all. It's an interesting perspective. It's what Friedman originally introduced when he first introduced Mars. Many people today would prefer to rely just on the test results. So what's interesting here is that once we have identified this sequence of models, we can actually have a nice review of them over here. What I did is I clicked on the Model Details and Selection button, and we have identified in color the two criteria, the two defined optimal models, one defined on the test R squared or mean squared error, the other defined on the GCV, and you can select any one of these sizes of models, and you can then see all the performance measures and details that we produced automatically for the best model. If you're happy with the best model, then you don't have to look at this graph at all, this display. But if you are wondering whether there might be another model that might be a little better than what we said was optimal, because you're willing perhaps to give up a little bit of accuracy in order to obtain a simpler model, let's just see what happens if we go with the 7 parameter model. Now, why am I choosing 7? It's just arbitrary. Let's just double click here and see what happens. So you can see over here that test sample's mean squared error is now up to 17.75. Why is that? Well, because we have fewer terms in the model, and everything in the report suggests that this model is potentially underfit, and we don't expect it to do as well, but if you decide you want to have a look at that, you have access to all of it. So if you're familiar with CART, when we have a decision tree and then we've grown the maximal tree and we prune back, we give you access to every one of the pruned subtrees, and you can make a decision and look at the details of any one. We've done exactly the same thing with Mars here. Okay, so that gives us really the basics for Mars. Now let's consider how might we make the model better or different. You've got some choices. Let's first go to options and limits. We said 15 was a default. Why don't we kick that up to 30? I don't have to do it this way. I could just type in 30. Let's just start with that as the one change that we're going to make. And now let's hit the start button again. And what you can see this time, it actually comes back with a slightly smaller model than the last time. And let's have a look and see what came out of that the final analysis, that's a little bit worse than before. What happened? Well, we started with a different maximal model, and the back pruning sequence actually chose a different path through the models that are available. And so the best model that we found last time wasn't visible this time. So it turns out that um, the size of the maximal model will determine which models are actually visible and available. And therefore, you will want to experiment with how you limit Mars as it builds its models. Let's now change one other control parameter. Let's go back here. I'll lower this a little bit. Let's lower this to 20. And let's increase the available interactions from 1 to 2. What does that mean? Well, 1 means this is the degree of interaction. And that means how many variables are allowed to interact with each other. 1 simply means that no interactions are allowed. 2 means that interactions are possible between up to 2 different variables, but not any higher than that. Let's again hit the start button and see where that takes us. And looks like over here we didn't do nearly as well. We got ourselves into an overfitting situation and ended up with a worse model. Okay, so it's just a warning. If what is going on when you allow interactions? Well, when you allow interactions, here's an interaction that we've created. Sometimes these 3D plots are not that easy to read, so let's go look instead at the definition of the model. And so we're looking here are the basis functions. So I will cut and paste this into another window. So here I've highlighted and I've done my Control C. Now I'm doing a Control N to bring up a new notepad from within SPM and a Control V to paste it. So now hopefully you can see it. You can see that we created a knot in the variable LSTAT, and then we created a knot in RM, which is the number of rooms in the house. And then what we did over here is we created an interaction between a knot in the tax variable and the first basis function, BF1, which is the demographic profile of the population in the neighborhood. And so that is the interaction that Mars chose there, and then the backstepping, it ended up at this particular model. Okay, so you're going to always be able to look at the details of any model that we develop by clicking on that basis functions tab. Let's look over here, going back to our very first model that we developed. If we go again to summary, and then we go to basis functions. Oh, it's giving me, let's choose the right model. I'll have to use my arrow keys, I think. Okay, now we hit the summary button. You can see we've got the 15 basis functions in the model. Interestingly enough, also, if you look in the left-hand panel, the number of predictors are 9, but we've got 15 basis functions constructed from them. Now let's look at the basis functions. Again, to make it visible, I'll cut and paste it. You can't change the font in this particular display over here. So a Control C, a Control N, and then a Control V, and now you can read it. And let's scroll up. Okay, so here are the basis functions that we've defined. Here is the model that was built. And then this expression over here is a convenient way of setting up the model so that if you wanted to refit it, you could use these expressions over here to create these variables that Mars has suggested, and you can use this model setup over here to make it convenient to refit that if you wanted to, perhaps on different data, perhaps on the same data, and you just want to get some additional reporting, you want to run it through some macros that you've got set up in another system, for example. Also, one of the things that some people do with this particular modeling technique is they will edit these particular points over here, the not locations, because these are the ones that Mars created, and you may want to tweak them a little bit. Instead of a pupil-teacher ratio of 12.6, you may want to have 12.0 instead, and then go ahead and build that model. If you tweak these things a little bit, normally you wouldn't expect any noticeable deterioration of the model, and of course you always have the chance that it will actually get better. All right, again, we'll close this window without saving it, and let's close this one as well, and let's go back to our modeling technique over here. And what I want to call attention now to is this battery tab, which was not mentioned at all, I don't think, in the last introductory session. The battery tab is, for us, when we do our modeling, perhaps the most important tab that we have in our software. It's available for every engine, and what it does is it runs experiments, pre-defined experiments for you. And the number of batteries available will be different for each of the different engines. I believe that when I checked here, if I remember my count right, there are 28 of these built-in multiple model builders for the Mars model. Let's look at this one over here, LOVO. Let's just try that. LOVO means leave one variable out. So what we're going to do is we're just going to run an experiment that I think many of you have heard of. Start with the same set of models, drop one, rebuild the model, and then rotate through the entire list just to see what would happen if you restricted access by just one variable. So we'll just hit the start button, and here is what a typical battery summary looks like. What we have, we're looking at the mean squared error as defined for the test sample, and we're looking to see what happens as we remove different variables. And if we click over here, we can now sort this, and it'll tell us what would happen as we remove these the variables that are available to us. Okay, so by the way, over here, the error profiles, these are those curves that we saw, and you can see that they all show roughly the same shape, but they're sitting at different heights after they get through the first few basis functions. Okay, one other interesting one that I'm sure many of you will be thinking about, and that is bootstrapping. We have two types of bootstrapping built in. This is the first one. Let's set up the battery options. Here, well, why don't we do 100? Otherwise, we're just going to let everything else remain as before. We won't build a reference model. We already have a reference model. And then let's just click OK. And now let's just start. So, what is the purpose here? We're just trying to get a sense of what is the variability around our performance measures. We can look at a lot of different aspects of the model and study the variability, but this is what we're focused on here. Notice the train and the test partition have been organized so that the test partition always has the same size. But the composition of that test, sorry, we did I misspoke here. It's a fixed test partition, but the train partition has now been built by bootstrap sampling from the original sample, training sample. So you can see here we get a mean of about 16 for the mean squared error, so that's a little bit higher than we saw when we ran the model before. and there's quite a bit of spread. We look at the fifth percentile, and you can see the result is at 12.9, and then let's look at the 95th, and we see over here it's at 16.2. So here it's still very comfortably below what we saw for the linear regression. Okay, there's a lot more to say about Mars. Let me go to one of the slides here just to focus on a particular point. And that is this. Keep in mind, Mars does its own variable selection. What you specify when you identify the predictors are not the variables that must be in the model, but the variables that are allowed to be in the model. Mars actually makes a decision as to what to use. Mars also automatically handles missing values. We didn't have any missing values in the Boston housing data set. What Mars does, it creates a missing value indicator, a 0, 1 variable. It creates those automatically, and those are the way in which it gets a variable into the model. That MVI comes in first, and then it will be interacted with the variable. What that means is that a sub-branch of the model is developed in order to use a variable that has missing values. So it can be very convenient if you've got a bunch of missing values and you really don't want to be bothered with what you're going to do about them before you get started. You can just let Mars use its methodology and review the results. You may not want to stick with those results, but you're not prevented from building a model that uses all the records in your data set straight out of the box. Mars will detect interactions, as we saw very briefly. All you have to do is to allow them. And the degree of interaction is something that you'll also have to decide. Mars transforms all the variables before it uses them. So you will see the model as constructed out of these things called basis functions. You'll have to look up what the definition of the basis function is. Mars will never use a variable prior to transformation. Sometimes the transformation leaves it identical to what it started with, but there's always a transformation process first. We also point out that Mars can be used to model the 0, 1 binary target as well. Sometimes it gives really very satisfactory results that way. So it's always worthwhile trying. Just a couple of comments on limitations. Mars is not very good with a huge number of available predictors. I would not want to use Mars even with a few hundred predictors. What I would do in that circumstance is use another methodology. We happen to prefer using CART or TreeNet or gradient boosted trees or random forest in order to do the variable selection and then run a Mars model on the subset of predictors. I personally try to keep that upper limit for a Mars model at about 50 variables. Also, if you've got a few variables with missing values, then Mars actually handles those very elegantly. If you have lots of variables with missing values, then Mars gives you models that can be difficult to understand. And we don't have time to explain why, but we found that to be a limitation there. Okay, so now we're going on to our second part of this session, and we're returning to the regularized regression. So we've posted a link available to you to the original paper by Hurl and Kennard. Hurl actually wrote about the idea of the ridge regression in 1962. His goal there was to simply stabilize the solution for a linear regression when there was very high collinearity among some of the columns. And so it was a technical trick. That trick has been used in many other circumstances where that kind of matrix, which is being inverted and then being used for hill climbing. So it's very well known as a computational device. But in 1970, they wrote a paper which linked it very tightly to statistical theory and statistical thinking, and they explained exactly what they were doing and the motivation here, which was the idea that you might actually not want the least squares unbiased estimate of the coefficients for a variety of reasons, one of which was even though the methodology gives you unbiased, which means uh, on average, with many, many tries with different data sets, you would average to the right answer, but in any particular data set, the probability that the betas, the coefficients that you're estimating, would be actually very far from the truth. So it doesn't do you very much good to know that if you were to repeat this experiment with different data sets many times, on average you would be right, but in any single um, modeling exercise, you would either be way too high or way too low. And so one of the ideas of the ridge regression was, how about if we gave you a method that would never, on average, be right, but would almost always be very close to what you're looking for? That would be very preferable. So that was the main idea there. They pointed out just a couple of situations where, not just a couple of situations, but a set of problems that they were regularly encountering, one of which was they noticed that their results were very unstable from sample to sample. They were working with engineering problems. Second, they knew a lot about the particular processes that they were trying to build models for, and they were therefore very confident when they saw coefficients that were too large. They were very confident that those coefficients were not right. They also encountered situations in which the sign on a coefficient in the model was wrong. So again, anybody who has had a lot of experience with building this kind of model has had this kind of experience where you look at a model and you simply say, I just don't believe it, this can't be right. Or you may be saying, I really hope it isn't right because I've basically staked my career on something being different. In any case, what they suggested and what can work pretty well is this technology of regularizing the regression, which will give you far more satisfactory results. What's interesting here, just to point out, is that the modeler now again becomes front and center. It's not just push the data through the machine and then accept what the oracle tells you. There's this bringing together of your own judgment and your own prior experience perhaps, or just common sense, along with looking at the models and then finally making an optimal decision. Okay, so that was the ridge. What came later was the lasso, which stands for least absolute shrinkage and selection operator. That was introduced by Rob Tibshirani, who's now at Stanford in 1996. He was at the University of Toronto at the time. And just a historical note, I think many of you do know that we started working with Leo Breiman and with Jerry Friedman in 1990. We worked with Leo all the way until his death in 2005, and Leo is one of the co-creators of CART and of Random Forest. And so it was one of Leo's ideas that was an important precursor of the lasso. Tibshirani does talk about that. And Breiman ran a series of simulation studies in which he showed the potential for improved prediction via selection and shrinkage. His methodology wasn't quite right. It didn't always give you what you wanted. The lasso performed much better. So the lasso has totally replaced Leo's original precursor, the non-negative garrote. Anyway, let's go ahead here and see. Okay, so what I want to do now is go back to my live session. And what we're going to do here is go back to the modeling dialog. And now go to the GPS generalized lasso. And we're going to, again, just check to make sure that our testing is the same as before. I routinely do that because sometimes you can inadvertently change it. And then, of course, if you do change it, it's going to be difficult for you to compare the results from one run to another. So just think of it as a bit of healthy paranoia. Look at the GPS controls. There's a lot going on here. At the moment, what I'm going to suggest is we're going to ignore all of this. We're also going to ignore the GPS Advanced tab, but we'll be coming back to that very shortly. So let's go ahead and just hit the Start button and see what GPS wants to do with this data. So we have a graph that looks just like, or very similar to the Mars, in that it's tracing out a pattern of increasingly more complex models along with a performance measure here. But there's some complexity that has been hidden. And if we want to see how we actually arrived at this curve, then what we want to do is hit the All Curves button. So let's hit that. If you're only interested in, hey, give me the best model, I don't care what it is, just spit out something that the machine has determined is the best that it can do, it's not that good here. We can see that that's got a mean squared error on that test sample of 21, so better than the least squares, but not better than the Mars model. It looks apparently definitively worse than the Mars model. But anyway, GPS cannot transform variables. It just takes them as they are. So if you really maybe wanted to do better than the Mars model, we should start with the variables that Mars created. But at this point, we're starting with the raw variables. So let's hit the All Curves button. And what do we see here? By default, we build 4 different kinds of models. And I'm going to explain what they are momentarily, but we call them the compact, the lasso, the ridge lasso, and the ridge regression. And it turns out that the ridge regression is the winner, and it achieves the lowest mean squared error on the test partition. And the curve that we see, if we click on All Curves again, that will undo All Curves. This curve that you see over here is the lower envelope of these curves over here. So we started over here, we drop down, we go all the way to the end, and then there's a little drop again at the bottom that's hard to see. So you can see the curve is starting in the close to the 30 neighborhood. We ignore this very inferior start of the ridge model. The ridge doesn't get good until the end. So we're really taking that curve from this point over here. Okay, so let's look at the best model summary. That's going to be comparable to the summaries that we got for the regression and the Mars. So these all are intended to look the same. Let's go ahead and have a look at the residual box plot. And you can see here, if we can go back to one of these others and bring them side by side. So that was the regression. You can see that interquartile range of 4.6 for the regression, and it's 4.05 for the GPS. So it's clearly been able to reduce at least the spread in the central area. We do have a bigger outlier over here than we had in the regression model, but still the average squared error is still lower. Okay, so going back over here, let's see what else we can learn. So I'd like to press the detailed solutions. The detailed solutions show us basically a set of choices, and these are models that are selected from a very large number of models that were actually built. The deeper green is showing the best result in the column. The first columns are all learned, so we don't care about those, and the second set of columns are the test results. So you can see if we're thinking about mean squared error, then the best solution is this ridge with 13 variables. It's a solution number 184. I'm going to explain that a little bit later. If we were interested instead in mean absolute deviation, then we would want a slightly different solution. And this one over here, it's the relative absolute deviation. That's so unstable that we don't really pay much attention to it unless we have some reason to believe that in that data set it isn't going to suffer from instability. But it's there for those people that are interested in that percentage absolute deviation measure. Okay, so we have some choices here. All you have to do, I'm not sure whether, I think we can double click on one, but maybe not. Yes, if you double click on a row, then you will get the details that come from that particular model. Okay, so let's go back to our main display over here, and let's click on the coefficients. After all, if you are a regression modeler, I don't think I can make this font bigger. So what you have over here are the 4 solutions that were best for each strategy of model building. You can see they do have rather different performance stats. They're choosing either different variables. The lasso and the ridge lasso are choosing the same variables but with slightly different coefficients. Turns out that compact and ridge choose almost the same set. There's only one variable difference. This is pretty unusual. Usually compact chooses a very small subset of predictors at the expense of not doing nearly as well. And now you can eyeball these and just decide if there's anything there that you are liking or not liking. One of the things that's quite dramatic over here is that there's a coefficient of minus 19 on the compact solution, and it is about minus 5 in the ridge model. One of the things to remember about a ridge regression, it tends to make the coefficient smaller. You're guaranteed that the sum of squared coefficients, we're not talking about squared errors here, the actual coefficients, if you square the coefficients and add them up, the ridge is going to give you a smaller sum of squared betas than the least squares. That's one of the things that it's designed to do. And on average, but not necessarily for every beta, they will get smaller in absolute value. And so that's where the shrinkage terminology comes from. Let's see if we can make this small again. Okay. So, if I'm interested in the coefficients, what can I do to learn something about the confidence intervals around those? So what I'm going to do here is move to the GPS Advanced tab, and I'm going to use the upper and lower 5% of the distribution, and let's ask for 100 of these. If it's set at 0, which is the default, then we're not going to get that. Now what I'm also going to do is, let's do this to save time. Let's do this just for the ridge model, which we saw was best. And now let's run this again. Okay, so we just got the ridge model where the results are going to be for the bootstrap variation is going to be in the classic output. So let's just scroll up here a little bit. And we should have, let's just see, I'll have to try to find it. Here we are. So hopefully you'll have found this as well. It's buried in a fair bit of output here. But what you can see here is that we get a lower and an upper bound based on the bootstrap resampling. So what we did is we took a new bootstrap sample from the training data. We did this 100 times. We looked at what the results in terms of the coefficients, what those were. The percent selected here tells us whether the variable or what fraction of the 100 models that variable actually survived into the final best model. And what you can see here is that there's only 3 of them. The constant, of course, is always in. There's only 3 of the variables that survive in all 100 replications. Otherwise, you've got relatively high fractions, 88%, 91%. And so therefore, we treat that coefficient as 0 when the variable doesn't appear in at all. Okay, so let's go ahead and see where we are, since we're getting close to the end of the hour here. And I'm thinking we've already looked at this slide over here. Now let's go to a little bit about the GPS terminology, which is an extended elastic net. So there is a single parameter inside of GPS which governs the strategy that is used in order to build the final model. And that parameter is called the elasticity. When it is 2, that's over here, then there's no variable selection, officially no variable selection. In fact, there might be, but that's not what it's designed to do. It may end up excluding some variables, but in the way GPS does it. But it's intended to do just shrinkage. So that's the ridge model. If the setting of the elasticity is 1, then we are intentionally doing both selection and shrinkage. We are not necessarily wanting to use all the variables, and we are looking to eliminate some and shrink others. And the 0 setting is looking for a very small number of coefficients. In the literature, in Jerry Friedman's articles, you will see he does relate this to the concept of best subsets regression. The idea is the only thing we care about is the number of variables in the model, in terms of that's how we measure its complexity. We do not care about the size of the coefficients. In ridge, we care a lot about the size of the coefficients, and in lasso as well. Just to compare this to the elastic net, as some people have asked, our elasticity in GPS can take on any value between 0 and 2. This is a real number. I mean, there's no point in fiddling with the second decimal place, or certainly not the third decimal place. So you might think of using elasticities that go from 0 to 2 in steps of 0.1, and this would give you a good idea of what the different options are. The range between 0 and 1 is actually very important if you are working with a relatively large number of predictors and you expect that only a relatively small number of those should or are desired in the final model. So when that ratio of variables that should be selected to the number of variables that are available, if that ratio is quite small, you want to be using either the compact or variations of the compact. And so in particular, coefficient elasticities between 0.5 and 1 can turn out to be very important for you. So here, this is a technical slide. Those that have dipped into the literature are very familiar with this. We are penalizing the regression. What that means that a fit is not considered the poorness or badness of fit is not just the sum of squared errors, but there's another component which could be the sum of squared betas. That's the ridge. Or it could be the sum of the absolute value of the betas. That's the lasso. Or it could just be how many betas are in there. That's the compact model. So that penalty, along with a factor that scales it up or down, that's really how the solution is sought for. One other really important thing, GPS is forward stepping. The original lasso was, the solution for the lasso was backward stepping. If you start with 1 million variables in the model and you're going to backward step, you're going to be doing an awful lot of computation. So the brilliance of GPS is that it actually allows you to get arbitrarily close to the true lasso solution, but forward stepping instead. And therefore, you can get very fast performance. We have a reference here to the two papers that lay out Friedman's thinking on that topic. So I think that we've gotten so close to the end. These slides are going to be available, or they even are available now online. You can download them. There will be further recorded video sessions in which we walk through more of the details of both Mars and GPS, and some of those sessions are actually several hours in length, so you can really get into a lot of the details if you would like to do that by video. So let me just take you over here to the last couple thoughts. How do you select the best model? Well, I think, just to repeat, you've got your own requirements. For example, we worked with a client that required certain optimal solutions to be computed in a very small amount of time. We're talking milliseconds because it was real-time online performance. If that's a constraint, and so you say, well, my job is not to find what is essentially the truth, but to find something that performs well and performs fast enough, then you may be looking for a solution that's very small, and this particular technology is going to help you do that. Obviously, you also can be bringing your own judgment in order to try to guide yourself to a set of coefficients that meet certain expectations. There's a clear room for judgment over here, but I don't think it's any more than is actually used in traditional modeling by traditional statisticians. So, what's next? In 2 weeks from now, I'll be with you again to discuss other tools for regression that are vastly more flexible than even what we've seen so far. We'll start briefly with regression trees, move on to ensembles of regression trees, which is the bootstrap aggregation, Leo Breiman's contribution, then Breiman's random forest, which you can think of as bootstrap aggregation perfected. We have Jerry Friedman's TreeNet, the gradient boosted decision tree, but focused on regression. And then we're going to end with some very elegant hybrid models that take the best ideas from trees and the best ideas from the generalized path seeker and put together some models that are really quite extraordinary in comparison to what anyone has seen before. So we'll be talking about the ideas 2 weeks from now, and then in 4 weeks from now, we will go through those same ideas with a hands-on session. What you need to do next, if you want to pursue this further, of course, is to visit our website, download and install the SPM software, request an unlock if you want to go more than the automatic few days that the install will give you. And then we are trying to answer questions that have come to us in real time now. There'll be further questions that we will answer to you by email over the course of the next few days. And again, we really appreciate your taking the time to listen to what we have to say, and we look forward to hearing from you. And we do want to know if you have any difficulties in working with this software or understanding it. Our goal here is to help you master this kind of technology and make good use of it. And obviously, we'll be very interested to hear of your experiences, and especially, of course, we want to know both the goods and the bads in terms of your successes and where the tools seem to work well, and if they don't, we would like to hear about where and when that might occur. Thank you again, and signing off till 2 weeks from now.